Hello everyone. In the previous video, we said we can think of the Fourier series, the mathematical technique, as a system where the input to the system is a periodic signal x of t. And what the Fourier series do to us is it take the signal x of t and decompose it to its harmonic. Basically, it will show us how much DC present in this signal x of t, the lowest frequency, the second harmonic. For example, this could be the lowest frequency 100 Hz, the second harmonic will be 200 Hz, and the third harmonic will be 300 Hz. So it will show us how much of this frequency present in this signal, what's the strength, what's the delay, the highest frequency, and so forth. I can represent x of t as a linear sum with amplitude dn that show how much strength, what's the strength of the signal, and dn is usually complex. It has magnitude that express the amplitude, and it has phase that express the delay. For example, this is how much delay for each harmonic. Or the compact trigonometric, which is more obvious to us, it's basically a DC C0, which is this DC, and harmonics, cosine function of different frequency, omega 0, that will be the fundamental frequency. And N1, that's the first harmonic. When N2, that's the second harmonic. This is N. When N3, the third harmonic, and so forth. We cannot directly calculate Cn and C0, but we can calculate Dn, and after we find Dn, we can find easily C0 and Cn. And the relationship between them is C0 equal D0. And Cn equal twice the magnitude of Dn. And theta n is just the angle of Dn. Remember, we said Dn is a complex usually. It has a magnitude and phase. If we want to know this relationship, how do we get it? What you can do is we're going to expand this exponential form. And when we expand it, and I will expand it only for n equal minus 1, 0, 1. Then x of t will be something here plus d minus 1 e minus j omega 0t. Plus when n is 0, that would be just d0. When n is 1, that would be d1 ej omega 0t, plus when n is 2, so forth. Now, d is really going to be complex. It will have a magnitude, and d minus 1, it's always going to be the conjugate of d1. That means the magnitudes are the same, but the phase are negative of each other. So that means this will be negative of this phase. Alright, so I can express d minus 1 as d1, and the exponential is e minus j theta 1, the angle, e minus j omega 0 t plus d0, and this term d1 will be the magnitude e j theta 1 times the exponential e j omega 0 t plus for dn and so forth. Now these I can combine them, d1, and this will be e minus j omega 0 t plus theta 1 plus d0 plus d1 e j omega 0 t plus theta 1 plus and so forth. And the d0, I will bring it just here, and I will combine these two terms, and this will be d1 e minus j omega 0 t plus theta 1 plus e j omega 0 t plus theta 1. Now if I divide this by 2 and I multiply here by 2, then this can be 2 d1. Now this whole thing here is cosine. Use the trigonometric. And here this term is just c1. So that will be c1. When n is 1, that's c1. Cosine when n is 1, that will be omega 0 2 plus theta 1. So that is theta 1, and that is omega 0, and this is c0. You can use this relationship after you calculate dn, which we will show next example. When you calculate dn, then you can find c0 cn theta n from dn using this relationship. Again, for Fourier series, you can think of it as follow. You have a signal that is periodic. You take it to the Fourier series operation. This will give you the component present in this signal. So if I add these two, I will get back the original signal, this. And that's what the Fourier series operation. Let's take an example. This example, they use it in pulse communication. What they do is the pulse width here, tau, for example, could be, let me expand it a little bit so you can see it. So tau in this case could be 1 nanosecond, and t0, the period here, could be 1 microsecond. So that means every 1 microsecond they transmit a pulse, and that's how digital communication. In this case, that the speed of this transmission will be 1 million pulse per second. If t0 is nano, then that would be 1 giga. So you have this periodic signal. Now the question is, I want to know what are the frequency content in this signal, so I can figure out how much channel bandwidth, the medium, how big is the medium should be to transmit this digital signal, these pulses. Well, we're going to use the exponential. So we know that dn equal 1 over t0, the integral over a full period of the signal, e minus j n omega 0 t dt. Remember, omega 0 is 2 pi f0, and this will be 1 over t0. Now, when you integrate over a full period is from here to here, or from here to here. So I will integrate over this full period, because then I will use only one integral, versus I choose this period. Then that means I have to integrate from 0 to tau over 2. From tau over 2 to here, the signal is 0. Then again, from that point to t0, the signal is a, which is two integrals. So that's very important to decide which period do you use. So now the signal equal a only from this range to this range. So that will determine the limits of the integral. So from minus tau over 2 to tau over 2. Students sometimes will make a mistake and they make these from minus t0 over 2. Well, from minus t0 over 2, the signal is 0. So the integral will be 0. So you only integrate from where the signal exists. And the signal a, e minus j n omega 0 t dt. And if I integrate this 1 over t0 without making any mistake, hopefully, that will be a over minus j n omega 0 e minus j n omega 0 t from minus tau over 2 to tau over 2. And this will be a minus j n omega 0 e minus j n omega 0 tau over 2 minus e j n omega 0 tau over 2. Minus here will cancel this minus and you get plus here. The next step, I want to make this like a sign. So what I can do is the minus here will multiply inside here. So this will be a over j n omega 0 e j n omega 0 tau over 2 minus e minus j n omega 0 tau over 2. I will divide this by 2 and then multiply here by 2. So this term will be now sine. So then this will be a 2 over j n omega 0 sine n omega 0 tau over 2. And that's what's the n. I can express it further in a sinc function. That will be 2a sine n omega 0 tau over 2. And I have here n omega 0. I need tau over 2 here. So I'm going to multiply here tau. I multiply here tau. I will bring these two down here. And I will take it from here. So now this is a sinc function. This one here is a sinc function. So this is just a tau. You know, I told you guys, hopefully I will make mistake. I already see a mistake. Probably you wonder where is the t0. What happened to that t0? It's here, but suddenly it disappeared from here. So we have it here, and 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 here. And that's your final answer. So we found the Fourier series coefficients, dn, for this periodic signal. And we can express this periodic signal f of t as a linear sum of dn, which is in this case tau, over t0, sinc n omega 0 tau over 2 ej n omega 0 t. ej n omega 0 t, this is a sinusoidal with different harmonic n omega 0. If we want to plot dn, this is the dn for different harmonic, and let's plot it for t0 pi and tau 0.1 pi, then that will be the plot. It's a sinc function. This will be d0, so that will be this one. The next one will be the first harmonic and so forth. Just to review the sinc function, remember sinc x is just sine x over x. In communication and in many cases they want the main loop. What is the frequency of the main loop? That means from here to here. Those are the important frequencies. All other frequencies like those are usually small and we can delete them. So if I want to find the main loop, that means it's the first time the sinc function goes to 0. So it will be 20 radians per second. That is the first time the sinc function goes to 0. So how did we find that? Well, that's coming from dn. Let's find the sinc n omega 0 tau over 2. When does it, the first time it goes to 0? Well, if we look here, the first time it goes to 0 when x equal pi, because sine pi is 0, or 2 pi, that will be the second 0, or 3 pi, 4 pi, because sine n pi will always 0. So that means if I want to know this function, when is the first time it goes to 0, the argument n omega 0 tau over 2 equal k pi, where k is 1, that will be the first 0 here, when k is 2, the second and third. So let's press the when k equal 1, that will give us the first 0 here. So then this will be n omega 0 2 tau equal pi, and I need to solve for n omega 0. Those are the harmonic, because remember this axis here is n omega 0. It's the frequency, but it's not continuous frequency, it's discrete frequency. It has only omega 0, 2 omega 0, 3 omega 0, and so forth, where omega 0 is the fundamental frequency. So let's solve for n omega 0. Then n omega 0 will be 2 pi over tau. For this case here, the first case, if we chose tau to be 0.1 pi, then that will be 2 pi over 0.1 pi, and this is 20. So our first 0 will happen here. So our first 0, 20 radians per second. Now, which harmonics is this? Is this the 7th or 8th or 9th harmonic? Well, that's easy. I can solve for n. Now, n equal 20 over omega 0. And if t0 is pi, then omega 0 will be 2 pi over t0. And you plug for t0 pi, that would be just 2. So omega 0 is 2. So now that would be 20 over 2 is 10. So this 20 radians per second is the 10th harmonic. And here omega 10, the 10th harmonic. If you count, that is 1, 2, 3, fourth harmonic, fifth harmonic, sixth harmonic, seventh, eighth, ninth harmonic, and the 10th harmonic. And if you delete all these frequency component of this periodic, that means I carry out the summation here. I carry out this summation here from minus 10 to 10. And I sum up these terms. So only 10 harmonic. F of t, this signal will look something like this. Why? Because I deleted all high frequency, and usually the high frequency cause this edge. So I'm missing this edge. So my signal now from only 10 harmonic will look like this. And for communication, that will be fine, because all you have to detect is there a pulse or not? You don't care about the edge. In image, the equivalent, if I have an image and I deleted high frequency, the edge in the image will be blurred out. In a speech, you will hear like the speaker talking in a big room. It will not be crisp, sharp. If I use only N4, that means 4 harmonic, N0, N1, N3, N4, and I ignore all upper harmonic, and I add them up, I will get this signal. It doesn't look really as this signal. Now, if I add 100 harmonic, that means N goes to 100, and I add all the sinusoidal, then that's how this signal looks. And it's very similar to our original signal here. Okay, so let's go back now and look at this example. This is another important example. This is an impulses, and we use this train of impulses to sample a signal. And when you look at this is a periodic signal. So we should be able to use the Fourier series and find what are the harmonic or the frequency content in this signal. And we're going to use the exponential method. So in this case, dn will be 1 over t0, the integral over a full period of the signal, which is an impulse in this case, e minus j n omega 0 t dt. And the integral of this one is 1 over t0. Before I integrate, an impulse multiplied by any function, it's the sampling of the function at the location of the impulse. This impulse located at t equals 0. So I will get the impulse back again, and the strength of it will be the sample of the signal at 0. And this is just 1 over t0, integral of t0, the impulse. This ae to the power of 0 is just 1. And the integral of an impulse give you 1. So that means dn is 1 over t0. So it has the first harmonic, second, third, fourth. Their strength is just 1 over t0. And Cn in this case will be 2 the magnitude of dn. So that will be 2 over t0. And dn is always going to be positive. So the angle of dn, since always a positive, is 0. So I can express then the signal x of t in the exponential form in this way. dn, in this case 1 over t0, e j n omega 0 t, or I can express it in the compact trigonometric, which is c0, which is 1 over t0, plus the summation n from 1 to infinity. Cn, that's in this case, Cn is 2 over t0, cosine n omega 0 t plus theta n, which is 0. And that will be the expression of the signal in the compact trigonometric. And that is here. All right, now the next one is Parseval's theorem. Parseval's theorem basically it tells us how do we calculate the power of a periodic signal. This is the definition of the power, and we learned it in earlier chapters. Now we said if we're going to express the signal in the compact trigonometric, and they ask you what's the power of these compact, well, a DC, the power of a DC is just the DC squared. A power of any sinusoidal with amplitude Cn will be the amplitude squared divided by 2. So then the power of this one will be just Cn squared divided by 2 or multiplied by half. And that's how you find the power if you have these Fourier series coefficients. Same thing, I can find the power if I have the exponential Fourier series coefficient, d0 and dn. Just plug for Cn to dn and you square it and you should get these terms. And sometimes the criteria, when do I eliminate high frequency? Well, I may say I need the power of the reconstructed signal preserve 95% of the power of the original signal. Then you can use this criteria and just add harmonic until you get 95% of the power and eliminate all higher harmonics. Now, we can use the Fourier series in system analysis. In this case, if you have system, and we discussed this before, if I have a system and the system is described by its transfer function h of s or the frequency response h of j omega, and I have an input that is exponential, what is the output? Well, it will be the system response to this frequency, omega 0. So that will be this. So this could be a filter. How is it responding to omega 0? Omega 0 could be 2 pi 1000 and time the input signal. So this system, all it does, it will either amplify or attenuate the input signal. Now, if I have any periodic signal, like the recording of the vowel E or I or O, so I can express it in the exponential Fourier series this way. And this signal is going to this system, and I want to know what's the output. The output will be exactly the input, which is in this case this and the summation, multiply by the system response to the different harmonic present in the signal. That means the system response, when n0, that's the DC. When n1, the first harmonic, how does it respond to the first harmonic, second harmonic, third harmonic? And that will be this term here. That's the system response. So the output going to be exactly the input, which is this summation and this, amplified or attenuated by the system response to the different harmonics. So we can use the Fourier series to analyze.